Hello everyone, this is Mauro Lucchini and Laura Vicario presenting wireless energy harvesting for Internet of Things.
Firstly, we are going to see who were the authors of this journal article. After, we are going to see what was the motivation and the objectives. Obviously, we are going to check what was the development of the work done. And finally, we are going to analyze what were the results and conclusions of this work. In this slide, the authors of this article are mentioned, as well as the journal on which the article was presented in June 2015. That is the IEEE Communications Magazine.
Now we are going to see the motivation and objectives of this work. The Internet of Things is an emerging computed concept that describes a structure in which everyday physical objects, each provided with unique identifiers, are connected to the Internet without requiring human interaction. Long-term and self-sustainable operation are key components for realization of such a complex network, and entail energy-aware devices that are potentially capable of harvesting the required energy from ambient sources. Among different energy harvesting methods, such as vibration, light, and thermal energy extraction, wireless energy harvesting has proven to be one of the most promising solutions by virtue of its simplicity, ease of implementation, and availability. In this article, an overview of enabling technologies for efficiency wireless energy harvesting and analysis of the lifetime of wireless energy harvesting enabled IoT devices were presented. Furthermore, a brief study of the future trends in the design of efficient wireless energy harvesting systems and research challenges that lie ahead are also mentioned. This article is also focused on the enabling technologies including high-efficiency wireless radio-frequency energy harvesting rectifiers and low-power wake-up radio for wireless energy harvesting units, a power management unit architecture that accommodates a battery charging scheme using the harvested energy through a wireless energy harvesting unit was presented. Moreover, the lifetime of the proposed wireless energy harvesting IoT system in the context of two common scenarios in IoT networked system was analyzed. The energy cost model was described using uniform and random distribution topologies of sensor devices. It is shown that the lifetime is increased substantially using the wireless harvesting techniques. Finally, the article concludes with a discussion of future research challenges.
Now, let's proceed with the development of the work. The wireless energy harvesting receives the transmitted radio waves with an antenna and converts the received RF energy into a stable direct current energy source to supply the sensor device. Wireless energy sources can be classified into categories: dedicated sources, which are the radio frequency sources deployed to provide a predictable energy supply to the device. Dedicated sources can be optimized in terms of frequency and maximum power to meet the requirements of the sensor devices. A sync node is an example of a dedicated source, whereas ambient sources, the second type, can be further divided into two subcategories. First, static or anticipated ambient sources, which are the transmitted that radiate stable power over time, but are not optimized, for example, in terms of frequency and transmitted power, to supply the sensor device. Mobile base stations, broadcast radio, and TV are examples of anticipated ambient sources. On the other hand, we have dynamic or unknown ambient sources, which are transmitters that transmit periodically in a fashion not controlled by the IoT system. Harvesting energy from such sources requires an intelligent wireless energy harvesting unit to monitor the channel for harvesting opportunities. Wi-Fi access points, microwave radio links, and police radios are examples of unknown ambient sources. The different ambient sources in these two subcategories may transmit at different frequency bands. Harvesting wireless energy at multiple frequency bands complicates the antenna geometry requirements and demands a more sophisticated power converter. Therefore, wireless energy harvesting is typically optimized to harvest from the dedicated energy source, for instance, silk node, and may be devised so as to allow ambient energy harvesting as an auxiliary source.
RF to DC rectifiers allow the conversion from the received radio frequency power to the usable DC supply that the device needs. However, this conversion comes with a certain amount of power loss in the matching circuit and in the internal circuitry of the power converter, which is evaluated through the power conversion efficiency. also known as PCE. PCE is an indication of the amount of harvested energy that is available for the sensor device. The available harvested power is given by a Friese equation and is directly proportional, as seen in the following equation, to the transmitter power, the path loss, the transmitter's antenna gain, the receiver's antenna gain, the power conversion efficiency of the converter, and the square of the wavelength. And it is inversely proportional to the square of the communication distance between the source and the device. A schematic diagram of the wireless energy harvesting unit is shown in the following figure. The transmission power, communication medium, antenna gains, and frequency of operation are typically dictated by the application requirements. Therefore, a viable design parameter to enhance the harvest power or maximize the communication distance is PCE. The PCE curve as a function of distant input power level for a typical rectifier can be seen in figure B. As shown, the PCE is optimized to peak at a certain input level that corresponds to a specific optimal distance.
The radio transceiver is typically the most power-hungry block of a wireless sensor device. Although the transceiver is rarely called into action during each operating cycle, it has to keep monitoring the channel. This idle listening process is a significant contributor to the overall power consumption of the sensor device. An efficient approach to address the idle mode energy consumption is duty cycling, in which the receiver on demand switches between listening and sleeping states. Among the different categories of duty cycling, synchronous, pseudo-synchronous, and pure asynchronous, the latter provides the most efficient solution in terms of energy consumption. In the synchronous approach, the sensor device is in deep sleep mode and only wakes up when signaled by the sync node or its neighboring devices through an interrupt command generated by a low-power wake-up radio. A wake-up radio is a simple receiver that receives the wake-up command and generates an interrupt for the main receiver. In a wireless energy harvesting device, the implemented rectifier, followed by a comparator, can perform a wake-up radio with minimal complexity overhead. The timing diagram of the asynchronous communication approach is shown in figure C, while the block diagram of a wake-up radio enabled sensor device is shown in figure D.
An integral part of any energy harvesting system is its power management unit. The power management unit is in charge of controlling the storage of the harvested energy, and it also manages the distribution of the available energy among different consumers in an effort to maximize the lifetime of the device while maintaining high quality of service. The architecture proposed is an event-triggered asynchronous scheme based on the signal generated by the wake-up radio. The power management unit architecture also detects preempts the failure of a node in the event of energy deficiency. A detailed block diagram of the power management unit for the wireless energy harvesting sensor device will be shown in the following slide.
The power management unit starts its operation by a trigger signal generated by the wake-up radio of the wireless energy harvesting unit, interrupt. The power management unit first activates the main transceiver through on-off and then sends a wake-up signal wake-up to the sensing unit to start its operation. The sensing unit toggles the stop run to hide, signifying that the power management unit is in running mode. The request signal indicates the amount of energy required by the sensing unit. The signals BAT and C indicate the amount of energy left in the battery device and the wireless energy harvesting unit storage element, respectively. Accordingly, the power management unit activates switch 1 through signal sense to fulfill the power requirements of the sensing unit. The sensor unit is in charge of sensing, data processing via microprocessor, and finally transmitting them to a lower power transceiver. The sensor device requires a minimum power to operate in sensing mode. When the energy in the battery device goes below a certain threshold, the power management unit sends a recharge command to the storage element by activating switch 2 of the wireless energy harvesting unit to charge the battery. Until the device doesn't recharge itself again over that threshold, it sends an out-of-service command to the sync node, signaling that it is going out of service. The sync node in turn sends a stop all services signal to the device and puts the device out of the sensing service loop, but keeps transmitting RF energy for harvesting. When the device is ready for service again, it sends a ready signal to the sync node, which in turn sends a resume all services signal to the device.
Now we are going to see the main results and conclusions of the work. The lifetime of an IoT system, battery operated only or battery with wireless energy harvesting unit, depends on the average energy consumption of the sensor devices per active duty cycle. This involves the combined operations of sensing, processing, and communication, that is, receive and transmit. The lifetime estimation for the sensor device operated with a battery assisted by a wireless energy harvesting unit can be formulated as in the equation below, where EB is the energy of the battery, CD is the weighted average of the listening, receiving, processing, and sensing energy. CTX and CH are the proportional constants for the transmission energy and the harvesting energy respectively. And finally, Rij are the distance of the device J to the sync node I.
Now, in the following slides, two different scenarios will be described in which the sensor devices are distributed in two different topologies. The first scenario, shown now, corresponds to a ring topology, in which the sensor devices are uniformly distributed around the sync node at a given distance. All the devices receive a similar amount of wireless energy for harvesting, assuming that the channel is static between the sync node and the sensor devices. The transmitted energy from the device to the sync is the same for all nodes. As it can be seen in the graphic, the energy harvesting green line increases the lifetime of the battery-assisted device by 30% for lower power sensors devices. The wake-up radio scheme enhances the lifetime by further than 110%, as depicted by the blue line. Setting the distance to the half black line, the lifetime of the device increases with a reduction in distance between the sync node and the sensor node.
The second scenario consists on a multi-hole topology where sensor devices are randomly distributed following a Poisson distribution. The first sensor node in the network only acts as a sensor and transmits its own data. However, the remaining nodes act both as sensor of their own data and relate for data coming from the further nodes. Thus, to compute their lifetime, it is required to add the energy consumption of the relay cycle to that of the sensor cycle. The estimated lifetime of the sensor devices in two-hop topology shown before is displayed in the following graphic. Energy harvesting extends the lifetime of the nodes. Node J1 is exercised twice as often as J2, so it consumes more energy and has a shorter lifetime than node J2. The lifetime enhancement through the wireless energy harvesting for a node at a distance similar to that of the ring topology is approximately 5 times larger, more or less 510% as compared to 110% in ring topology for low power sensor devices. Therefore, it can be concluded that for end-hop topology, the lifetime of the devices is further enhanced.
During the article, technologies and schemes to enable wireless energy harvesting for IoT systems have been overviewed, with an emphasis on improving the efficiency of the wireless energy harvesting unit and reducing the energy consumption of devices. The lifetime of the wireless energy harvesting assisted battery-operated systems in an IoT architecture are analyzed for two different scenarios. A study of the specific energy requirements of IoT devices reveals that achieving self-sustainability requires improved design techniques at both the circuit and system level.
In the following slide, we're going to see the future trends and the main research challenges. A wireless energy harvesting unit as an integral part of such sensor devices must comply with low cost and small size requirements. Efficiency is another crucial factor for a wireless energy harvesting system. High efficiency becomes increasingly relevant considering that the transmitted power by the dedicated source is usually limited due to health issues and interference constraints. The scenarios and the respective analysis in the article assume the channel as static and time invariant. Practically, channel characteristics vary depending on the environment in which the number of interferes and the number of paths available from source to that there are from the source device to sync. Harvested energy depends on the distance between sync and sensor node. In the presence of fading or multipath, the received energy for the purpose of harvesting and the transmitted data are adversely affected. Although recent development of energy harvesting technologies mitigates the energy scarcity issue, the sensor device still has to operate in duty cycle mode due to limited energy collection from the environment, and dynamically adjust duty cycles to adapt to the availability of environmental energy. Such dynamic duty cycles pose challenges for medium access control, layer protocol design in terms of synchronization, reliability, efficiency of utilizing channel resource and energy, and so on. Therefore, solutions of duty cycling aware middleware between MAC and physical layer power management are highly desired. Moreover, dynamic duty cycling also has non-trivial impact on the end-to-end performance of the network layer, including end-to-end delay, throughput, and so on. However, the current routing protocol designed for IoT has paid very little attention to duty cycling. Fueled by increasing in traffic and data demand, mobile technology is moving toward the fifth generation, where everything will be connected via the internet and accessed through the cloud. Relay techniques utilized by 5G can benefit wireless radio frequency energy harvesting. Also, smartphones, due to their mobility, can act as gateways and sync nodes, relaying data for sensors in personal area networks and as a source of radio frequency energy for harvesting purposes.
That's all from our part. Thank you very much for your attention.